In this video, we're going to talk about lists in Go. I've shown a picture here on a screen of what a list looks like in Go. So you have, for each node, a pointer to the previous node and a pointer to the next node. We refer to this as a doubly linked list. And then there's also a sentinel here. This is a node that's not really part of the user's data, but it's used to make the implementation simpler. So Go also keeps track of the length of the list. So here it's 3 because it's 3 nodes, not including this root sentinel. You can see going the previous around the circle and next around the circle. So this doubly linked list is also circular. They do that rather than using nils to make the implementation easier again. They don't have to worry about nil values. So why would we want to have one of these lists? Well, maps were great for looking things up fast, and slices were great for keeping things in order. But if I have a slice with, say, 500,000 million things, and I want to delete something in the middle, in order to maintain the slice, I'm going to have to slide everything over to the left, and that can get quite expensive. Whereas in a list, if I want to delete this node here, all I have to do is update the pointer from this one and the pointer from this one, and this has gone away. So deleting list node 1 involves updating the previous in list node 2 and the next here in the root sentinel, and so that's going to be much faster. So to demo this list package in Go, I've created a little cache simulator program. So in virtual memory, your computer can pretend that it has more memory than it does by swapping things out to disk. And so when you access a page of memory, the operating system will check if it has it in memory or if it needs to go out to disk and get it. Going out to disk is referred to as a cache miss. And the algorithm that's very commonly used in these cache operating systems is the least recently used. So whatever page was least recently used, we will kick it out if our cache is full. I'm going to do a tiny cache here just for the demo with a capacity of 3. And I have this pages.txt file. This will specify which pages that I'm accessing. So I access page 1, then 2, then 3, then 4. When I access page 4, that's going to be a miss. Well, all of these will be misses so far. But page 4, the cache will be full. So we'll have to kick out something. We'll kick out 1, which is the least recently used. So again, I'm going to read from a file. I'm going to use os read file, checking for the error. And then I am going to read the entire file at once rather than doing the buffered, because I'm not worried about lines. I'm just going to read the entire file. And then I'm going to split that into fields. So all of the individual numbers, we'll use the string converter package to convert each number to an integer. Again, checking for any errors. And then we'll add that to our page requests. All right, so page requests is a slice of integers. So we're going to just add each request to our slice of page requests. So now we're going to have our doubly linked list, and this is going to track the usage order. So we use list from container /list, and we make a new one. We're going to make that our queue. Also, so that we don't have to find things in our queue by walking the entire queue, which is slow, we're going to make a map so we can map from a page number directly to its corresponding element in the list fast. So a map from page numbers to elements in the list. We start with 0 hits and 0 misses, and we loop now through our slice containing all the page requests. We check in our map to see if that is present in memory. That's using our frames map. And we will get where it is and whether or not it's present. If it does exist, then that's what's called a cache hit. It's already in memory. We don't need to load it from disk. So we increment our number of hits. We'll print out hit. And we're going to move that to the front. So our list package is going to give us a move to front method, which will take the element. So that's one of the items in our list, right? So one of these nodes, and we'll simply move it up to the front of the list. If we didn't find it, then we need to load it in. If our list is full, then what we're going to do is we're going to take the last item in the list and we're going to kick it out. So we get its value. Now, one of the interesting things in the older versions of Go, they didn't have any way to do what are called generics, which we'll cover later in the course. So the value is of type any. So we need to take this value, which is of type any, and explicitly make it into an integer. So we get the value from the last thing, we make sure it's an integer, then we say, I want to take that last thing, so this final list node here, list node 3 in this particular picture, and we're going to remove it from the list. And then we're also going to delete it from our map because that page is no longer in memory. So we remove it from the list and we delete it from the map. We've incremented our miss number. Then we also need to take this new page and we're going to put it at the front. So push front is going to create a new one of these list nodes containing that page number. And then we'll also take that element which we've gotten and store it in our map so we can find it quickly. So then we'll print the cache state. So we loop through the list. So we start with the front of the list while our element is not nil. Doing e.next to move to the next one. And we append to our state, to our slice, the value from that. And then we're going to print that out. So we're going to print the page, the results, and the state. Then we're going to print out at the end this total. So you can see here, if we go, so when we start the cache simulator, it indicates it's simulating a cache with capacity 3. We look at the sequence of pages that will be requested. Page 1, 2, and 3 all miss and fill up the cache. 3 is up front because it was the most recently used. Page 4 is a miss. It will end up at front, and the least recently used one, 1, gets kicked out. 1 is a miss. It comes back in at the front. 2 is a miss. It comes back in at the front. 5 is a miss. It comes in at the front. 1 is now a hit and moves to the front. 2 is a hit and moves to the front. 3 is a miss and comes in at the front, pushing 2 and 1 back and kicking 5 out. 4 is a miss, coming in at the front, pushing 3 and 2 back, kicking 1 out. And then 5 is a miss, coming in at the front, pushing 4 and 3 back, kicking 2 out. 12 requests, 2 hits, and 10 misses.